what I would say, I mean, this is a technical course for the web scientists. I've been running this module for quite a long time now, and have been running it for groups where some people don't have a technical background, so whereas it may look a bit daunting to begin with, don't worry, I will get you through this. What this module is about is what's known by a number of names. So some people will refer to this thing as semantic web, some people will talk about Web 3.0, some people will talk about the web of linked data. This is all about looking at what you might say an evolution of the web from a web that mostly contains documents to a web that contains data that we can then do things with. So in terms of what I'm going to try and get us to do in this course, I first want to look at the ideas, the history behind semantic web. In terms of when the term was coined, it was first coined in about 2000 by Tim Berners-Lee. I think from what I remember, it was in a presentation at an XML conference. The semantic web, the technologies predate that, and the ideas behind it go back quite a bit further than that. So it's built on quite a strong heritage from the AI community, from the information front community. I'll talk a little bit about that in this lecture. What I want to do is to give you a feeling for the breadth of what the semantic web is. Now, the semantic web is still an active area of research, it's an active area of development and standardization. So I'll be going fairly close to the current state of the art regarding the standards which have been developed. So I think this year, I think I get up to about a year and a half ago. So we'll be covering stuff that's very recently gone through the standards process. There are some things that we'll do in this course. So part of it has a practical component. We're going to be using a language called OWL, the Web Ontology language, which is used to create formal descriptions of domains of interest. So a formal account of the things that we want to represent. For the time being, you can think of this as being a bit like a very advanced type of database schema. So there's a piece of design work that I'll get you to do. The advantage here is none of you have got any background in this, so this is going to be a bit of a leveler. And actually, most of the difficult bits here are not the technical aspects. They're not the technical aspects. The difficult parts of this are the conceptual design, trying to work out what matters in this domain and how you're going to go about representing it and the trade-offs therein. The final thing is trying to get across to you the direction in which the semantic web is moving and how it fits alongside the web. Now, can I have a show of hands? How many people here did web architecture last semester? Right. I owe you an apology, I've still got to return feedback. Yeah, well, as you can probably tell from the link, I've not been having a great time with it, so the good news is I can actually sit down longer than about half an hour's time. So, yeah, I've been trying to mark, but it's very hard to mark from the right and the back. So, getting back to this, the semantic web builds on the web. It uses all of the web technologies, it fits in the web architecture. So a lot of this will be trying to explain how the semantic web fits alongside these things and how the mainstream web can make use of the semantic web technologies. As I said, I'm the guy on the left. The guy on the right, Stefan Staab, will be teaching some of the lectures later on in the module. I need to confirm with him which one he's doing, actually. But last year he did about a third, I did the remainder of it. In terms of the way the module is going to be structured, 3 lectures a week, Wednesday, Thursday 4, Friday 10. I know that there is a Friday 11 that is listed in your timetables, or at least that's going to be listed. It's certainly going to be listed for the web scientists, basically, because the web scientists are coming completely not from a technical background. I've got an extra session in there just for them. Please don't all turn up to it, because you won't fit in the seminar room that we've got booked for it. In terms of what we're going to be trying to cover week on week, so running up to Easter, I'm going to go for a sort of a bottom-up approach. So this week is basically giving you an idea of the breadth of what it's about, the applications which it's used for at present, the sort of vocabularies that are in use. Then we're going to sort of build up through the different technologies. So first looking at the basic knowledge representation language, RDF, the resource description framework. Then looking from week 20 at how we can create vocabulary using that. Then we'll look at description logics and OWL to look at how we can create more expressive vocabularies. Then week 22-23 we'll be looking at the actual process of how you go about creating an ontology, how you go about creating a vocabulary. Week 24 is looking at the standard query language for the semantic web, Sparkle, and week 25 will be looking about how you would go about embedding these technologies into an application and what support there is out there for building semantic web applications in terms of the standards landscape. After Easter, things get a little bit less core. So first we're looking at some of the technologies that are used to embed RDF data into web pages. Then looking at things like rule languages, ontology mapping, so this is looking beyond the expressive capabilities of languages like OWL, and finally looking at a couple of use cases which are really on the cutting edge of where people are using this stuff. So there will be some material on streaming data, how do you deal with data when you've got too much to store, because there's some interesting results, but some interesting ongoing research in the semantic web community about that. And there'll also be a chapter looking at how people are applying these technologies to social networking. Now, in terms of the assessment for the module, two components, an exam at the end of the module, which is about 75% of the overall mark. 2-hour exam, standard structure for the paper, it's going to be 5 questions on the paper, you pick 3. And you'll get marks for the best, you get marks for the best 3. Please don't answer more than 3. The ontology design coursework is worth 25% of the overall. Now, given, if I go back a couple of slides, I've said I'll try and publish it in that week. I'll actually try and publish it by week 21. The thing is that there are some of the things in that coursework that you won't effectively be able to do until you've gone through this week. But I think it's worth giving you some early access to this. Traditional coursework is 30 weeks back after Easter, and I'll aim to get some feedback to you in the final week of the exams. Okay, so any questions about the sort of pragmatic bit of the course, the organisation of the course? All the slides you'll find online on the module website are effectively the same as the ones I'm going to be using this year. I may make minor changes to them. If there's anything major, I'll make sure that the major changes are on the website before I give the lecture. But I'm not anticipating needing to make huge changes to these slides from last year.
Are there any bits of software we worth downloading if you want?
There are, and I'll talk about those in due course. Well, in fact, if you look at the module website, there's a piece of software called Protégé that's worth downloading. But it will be a few weeks before you've got the necessary nous to know necessarily what Protégé is doing. So you could hold off briefly.
I've had a look at that before.
You've had a look at Protégé before. Okay. Any other questions? Yep.
The coursework is a technical one, right?
The coursework is a technical coursework. So what you will do for the coursework will be to create an OWL file, an ontology written in this language OWL. You'll do it with, I would recommend you do it with this particular editor called Protégé. You will submit that file, and normally what I ask people for alongside that is a text file with some Sparkle queries in that I've also asked for. But it is a technical coursework, it's not a report-based coursework.
For the exam,
components. So what I'm trying to get across from the exam is basically can you read and write these formats? Can you explain how they behave? Can you give examples? Can you show me how you would use them in certain places? It's that sort of thing. It is a relatively technical exam. I've tried to make it so that actually there's not huge amounts of writing required, but some bits of it I'm afraid people have to write for. Any other questions? Okay, right, what I'm going to look at for the remainder of this lecture, and this will probably be this lecture and a bit of the next one, will be to try and give you a very general introduction to the semantic web. Now, in terms of where semantic web came from, this is this is a book that Tim Berners-Lee wrote in '96, in which he gives a sort of an intuition for what the semantic web is going to be. Now, bearing in mind, this was published in '96. This is before the semantic web was named as such. By this point, however, there were the stirrings of the first technologies that came before the semantic web. So, as he says here, a goal of the web was that if the interaction between person and hypertext was so intuitive that the machine-readable information space gave an accurate representation of the state of people's thoughts, interaction and work patterns, machine analysis could become a powerful management tool. This is a very different view of the web to that which most people have. Most people's view of the web is that it's about putting documents online and letting people read them. The suggestion here is that actually, if we take those things and we structure them more so they're not just in free text, then we can start to do things with that data. We can start to reason with that data. When the World Wide Web Consortium started their semantic web activity, they went a little bit further than this. Now, this activity statement came, I think this is from about 2000, so there's a paper that Tim Berners-Lee, Jim Hengler and Ora Lasseter wrote for Scientific American in about 2001, which expands on this a bit further and gives us sort of a vision for the semantic web. But this definition I still think is pretty effective. So the point here, it's an extension of the web, it's not completely different, it's built on the web, but the point is we take the information on the web and we give it a well-defined meaning. And this, by well-defined meaning, I mean something whereby machines can understand what's being talked about. So, if we've done that, if we put data on the web and we've linked it together, we can make the web in general work better. We can make it easier for people to find things, or more effective for people to find things. We can automate some tasks that they might do. We can provide more effective information, interchange and reuse between sites and across time. The last piece is putting it in a nutshell. The semantic web is not the web for people per se, it's the web for machines. It's a way of using web technologies to allow machines to work together. Now, if we look at this and think about how this might work, there are sort of two different views. And one is to view the semantic web as being the existing web, but what we'll do is we'll put some annotations on it to explain what's going on out there. So we'll take existing web pages, we'll put annotations on them, we'll classify them. We might use things like natural language techniques to try and extract structured information from the natural language of web pages. And all of these annotations will make it easier for people to browse through the web and to search through the web. This view was, I would argue, the popular one from about 1997-ish through to about 2002, 2003. Within the UK, there was actually a big, 20 minutes in. Within the UK, there's an electronic libraries program that ran in the late 90s, whereby they've actually got librarians going out and trying to categorise and classify bits of the web, just as librarians would do this for books in a library. Unsurprisingly, it doesn't scale very well. The other view of the semantic web is to say, well, okay, let's ignore the existing web. let's ignore all that human readable text. Let's look at the structured and semi-structured data that we already have. We've got databases, we've got spreadsheets, we've got lots of things like that. What happens if we take those, we express them all in a common format, we explain the vocabularies that are used behind these things, so we express the database schemas in machine understandable format. What we can then do is put all this stuff on the web, use the hypertextual nature of the web to link these things together, and that then means that we can allow the integration of heterogeneous data across the web in ways that weren't necessarily anticipated by the people that originally put that data up there. The key to this piece is that if we're taking these database schemas, these vocabularies, and making it so that machines can reason about them, they can reason about the data, they can infer new facts from the things that they already know. Now, when the semantic web activity first got proposed in W3C, and those of you who've done web architecture last semester, I gave a talk on W3C there and talked about it being an industrial consortium, a group of companies who are getting together to agree on common standards for their products. There was a little bit of a bit of pushback from some of the members who looked at this and said, this is academic research, this is artificial intelligence, that's not what we're here for. This is all too hard, this is rocket science. And there's this business case that Tim Berners-Lee put forward that tried to say, actually, what we're talking about here isn't difficult because we've got all of these bits already there. So we already do things like build relational databases for data. We know how to do that. We've known how to do that for 30 years. We know how to build systems that can process queries. We know how to build rule-based systems that can infer new knowledge from existing knowledge. All we're trying to do here is provide a means by which those things can be put onto the web, or as he puts it, we're just webizing them. So, in terms of the broad objective of the semantic web, depending on who you look at, depending on who you read, there are very different perspectives. Some are that it's a very sort of highfalutin, pie-in-the-sky prospect. Others, it's a very down-to-earth thing. It's something that builds on technologies that we already have. Now, I've talked a little bit about where the semantic web came from. I've mentioned in brief that it's got roots in artificial intelligence, it's got roots in things like library information science. What I now want to look at is, in a little bit more detail, where the semantic web came from, because this goes a long way towards explaining why it looks the way it does now, and in particular, it gives you some very good understanding of some of the slight missteps that the semantic web has taken along. So I would argue that we've got sort of three separate themes that run through semantic web activity. Now, one is that it's a hypertexty thing, it's built on the web, but actually the view of hypertext that the semantic web embodies is a richer form of hypertext than that which the web itself uses. So this builds on sort of pre-web hypertext systems to some extent. There's a chunk that comes from a particular strand within the artificial intelligence community, knowledge-based systems. The first piece that was really evident in the semantic web community was the strand that came from the library and information science community. Now, these are the people that deal with things like information retrieval, that care about things like classification and categorization in libraries. And in particular, what they care about is metadata, and the origins of the semantic web lie pretty much in metadata. Now, by metadata, what I mean is data that describes other data, data about data. So, a web page is a piece of data, but the metadata for that web page would be things like who wrote it, when it was written, how big the file is, what media type it's in, all of those aspects of metadata. A library catalogue is a collection of metadata. If you go to the library catalogue, if you go to WebCat and search for a book, you get back not the book, you get back a description of the book. You're told who wrote it, who published it, when it was published, how you idea. It goes back to the mid-90s, around 1995. In the mid-90s, there was a bit of a moral panic in the States over the web. The web is corrupting our children. They should read anything on it. It's a terrible thing. It must be dealt with. We must provide access controls and parental locks for the web. And this was one of the ways in which the web community reacted to this was to look at the creation of a language called PICS, P-I-C-S, the Platform for Internet Content Selection, which was basically a way of describing a web page. So you could say, this web page has mild bad language, and it shows people drinking alcohol, but there's no nudity. And so the idea is that as a concerned parent, you could program your web browser on these different scales and say, you know, right, I want no nudity, I'm fine with it showing people drinking, but I don't want it to show people smoking, for example. And it would then limit what the web browser would show you. Now the point is that if you've got an infrastructure, a capability for describing metadata about something, you've effectively got a means for describing data as well. Metadata is just data. So the scope of the semantic web goes a long way beyond just the notion of bibliographic metadata or ratings metadata for web pages. We have an infrastructure for metadata, we can use it for more general purposes. And so this early technology PICS sort of came into the picture. The second piece that I want to talk about is the influence that the artificial intelligence community had on this. Now, within the AI community, there is this area of knowledge representation, which typically deals with things like logical-based representations, although there are other things out there. There are graph-based representations as well. So things like these frames. There are procedural representations out there like Shanks scripts. But the point is that within this area of AI, people care about how we can represent qualitative knowledge, basically factual knowledge, but in such a way that we can infer things that must follow from things we already know, and that we can represent both specific knowledge, so knowledge about particular individuals, particular objects, as well as more general things. You know, here is knowledge that we know about all mammals or all cats. These effectively allow us to capture some fairly complex meaning and reason about the reasoning that we're doing. Now, within the semantic web, the languages RDF, RDF schema, and OWL, the basic languages for the semantic web, are knowledge representation languages, and they draw on a 50-year-old history, probably close to 60-year-old history within artificial intelligence, and arguably they draw on another half century from within the philosophical community as well. So there's a long-standing thread that runs through the semantic web. And to give you an example of the sorts of things I'm talking about here, when we look at knowledge representation in AI, the standard thing that a lot of people look at is formal logic, first order predicate logic, things like that. And you'll see bits of that cropping up when we start talking about OWL. One of the other popular ways of representing knowledge uses what are called network representations. And in fact, this stuff doesn't originate with philosophers and logicians. This stuff originated with a chap called Quillian, who was a linguist, who was originally interested in trying to work out how human memory recall works. So he did sort of experiments in which he told people some facts, you know, canary is a kind of bird, all birds can fly, tweety pie is a canary, and then asked people, can tweety fly, and measured the length of time it took them to try and work that out. And so he came up with this sort of network-based model. So we have, you know, objects here, so a dog, Fido, barking, brown steak. We have relations between these things that are typed. So Fido is a dog, dogs bark, Fido has a colour that's brown, Fido eats steak. This is one way that we can consider the knowledge representation information on the semantic web works. As we get a little bit further on, we'll see how this fits in with it. The other thing that's happened within the KR community is this notion of what we call an ontology or a vocabulary. Now the thing is, if you have a knowledge representation language, a way of writing down facts, that's great, but it's not that much use by itself, because what you need is some way of being able to talk about the particular application domain in which you're working. So for example, if you're talking about bibliographic things, if you're talking about libraries, you want to talk about published works, authors, publishers, publication dates, those sorts of things. On the other hand, if you're talking about e-commerce, you want to talk about products and services and prices and orders and customers and so on. And so in each of these cases, what we can do is tailor to a particular domain by creating a vocabulary that's specific to that domain, an ontology, in other words. The final piece of this triad is the hypertext story. Now, for those of you who did web architecture last semester, you would have seen these sorts of comments. So hypertext, we're all pretty familiar with. We all use the web. We understand that the web gives us some non-linearity to the way that we both write and read. You know, we don't need to read things in order. We can jump around by following links. So effectively, we've got lots of text that are joined together that give us multiple pathways through them and multiple reading sequences. The web lets us do things like annotate and comment on things. I can write a web page that points to your web page and reviews it, for example. And there's also this notion that underneath there is a sort of underneath the links, there is an underlying association of ideas that's happening. So the links are merely the navigable manifestation of a more abstract relationship that happens between some concepts. So within the hypertext world, links are the thing that make it hypertexty. So you can view them as navigable links, you can view them as abstract relations. The point is that once we start viewing them as abstract relations, we can start talking about different types of relationships. So we can talk about this thing is authored by that thing. This is the home page of that person. For this thing, see also that thing. This thing is a definition of that thing. So we can type these links. Now this is something that we can do on the web, but most people choose not to. The point is, from the hypertext community, links are more complex than we see them on the web. They're not just sort of embedded links that have one start and one end. They can be multivalent. And the point is, they can be typed with fairly rich metadata about these links. Consider for a moment the relationship between a hypermedia system that contains type links and a knowledge net representation system that uses a network style of knowledge representation. There are both relationships between things. The difference I would say here is that if we look at hypermedia, we're sort of making links between bits of knowledge. For the network knowledge representation, the links that we're making when we say Fido is a dog, that is a piece of knowledge. What happens when we start putting types on hypermedia links? Does that make the links themselves knowledge? And moreover, if we can take the set of types of links that are being used in a particular hypertext, does that constitute a vocabulary for that particular domain? Does that constitute an ontology of links? Okay, so that's the sort of historical part. What I'll look at for about the next 10 minutes and then carry on in the next lecture is to start trying to talk about the basic concepts and some of the technologies in play. As I've already said, if we look at the web, as the web is constructed at the moment, the web is designed for people. So the information on the web is mostly through text, images, videos, things like that. Those are things which we can look at and we can mostly understand, but they're things that it's very difficult for machines to understand. And in terms of the technologies that we use on the World Wide Web, if we look at the sort of classic triad between a means for identification, a URI, a means for interaction, HTTP, the Hypertext Transfer Protocol, and a means for representation, XML, HTML. We've got the three components of the web architecture there. The semantic web is slightly different. The semantic web is intended to be for machines. So the point here is we structure the information so that machines understand it. We use all of the existing web technologies, but we add some extra things on there that will let us do this structuring. So these languages, the resource description framework, RDS schema, and the web ontology language out are ways in which we can structure data. The key difference between these things is that exciting. So looks like a line so there should have been a line there saying formal meaning is critical to understanding. These things give formal meanings to the data. Now I talked about this notion of machine understandable. It's worth at this point having a little sort of thought experiment to explain the difference between machine understandable data and machine readable data. On the web, the data there is machine readable. So it may be natural language, but we can take that information and it needs us to give it some sort of interpretation. What's happening here? Right, that was where I was trying to go to. Sorry, my clickers got confused. So machine readable versus machine understandable. If I take a language like XML, XML is machine readable format. What I mean by this is that I can parse an XML file, I can get an unambiguous document structure out of it. The point is the document structure I get has got no formal meaning. It's just a structure without semantics. There's been a lot of work that's been done with people trying to do things like define interchange formats based on XML. The problem is those things have to be, the meanings of those things have to be explicitly agreed every time you create one. There's no base level meaning that we can build on. So let's take this, and apologies to the web architecture people, I think I've seen these slides before. Here's a little fragment of an XML file with some nonsense words in. Here's the tree structure that you would get when you parse that. So these things are the elements, this is an attribute and its value, these things are bits of content data, bits of C data. What is this thing? No idea. What happens if I change the words that are used? So instead of having nonsense words for the names of elements and the names of attributes, here I've got words like order, part, quantity, customer, catalogue. So we could look at this and say, oh right, yeah, I understand what this is now. This must be some sort of e-commerce thing. Now here's an order with a reference number for a particular part, that's the part number, that's the catalogue it comes for, and it's an order for two of those things, and it's an order made by this customer. The thing that gave this meaning was you. So XML by itself is not machine understandable, machine readable, but not machine understandable. A language like RDF is machine understandable because not only can we get an unambiguous part and unambiguous structure out, there is some pre-agreed formal meaning to the structures that we get out. So we provide a base level of common understanding that we can then use to build interchange formats. So RDF by itself gives us the notion of classes and properties, and it enables simple types of inference, so we can do certain types of deduction that allow us to infer new things from knowledge that we already have. Right. In terms of the bits that make up the semantic web, there are some underlying principles, which are very much like some of the underlying principles you've seen about the web. The semantic web, like the web, is an open system. Anyone can make statements, assertions about anything. When we have things that we want to talk about on the semantic web, because the semantic web is just an extension of the web, we will use the same means for identification that we have for the web. We will use URIs. Most of, and I have to say this third point here is slightly blunted now, but most syntax that we can use to represent most semantic web things. And underlying all of this, we have a formal semantics. So that basically says, if you create certain XML-based structures, this is the agreed meaning for these things. So in terms of the set of technologies that go into this now, so this is a slide known as the Semantic Web Layer Cake. If you look out there, you can find about 7 or 8 different versions of it, all of which are by Tim Berners-Lee at different times. This is my version. I lost track of which version this corresponds to, but they're all more or less the same. The idea here is that we've got a bunch of technologies that form the semantic web that provide us with certain capabilities. They enable us to identify things. We have syntax. We can describe metadata. We can describe the categories and ontologies and do some sort of inference. And then there are things that sit above that. Some of these technologies are basically standard web technologies. So, for example, for identifying things, we use URIs, and now that we're looking at things like Unicode characters as well, we use international identifiers, IRIs. We have a standard syntax. We use XML, and we use the XML namespacing mechanism so that we can combine different XML syntaxes together. We have a standard metadata language, which is RDS, so this is our standard knowledge representation language that lets us make simple statements like Fido is a dog. But for us to be able to do things like define what we mean by dog or is-a, we need an ontology language, for example, like RDS schema or OWL. And we also have query languages that let us ask questions about the statements that we've made, so we can extract information from this. Some stuff that's, well, it is kind of standardized, but it's not widely used. There is some work on things like rule languages. You know, if this thing exists, then that other thing must also exist. This has been an area where the academic community has been far more interested in it than the commercial community has been interested in it. The industrial side really hasn't cared too much about rules, and there are still some sort of interaction problems between those and the rest, which is why I've sort of put those in a dotted box. All of this stuff so far has been through the standards process. There's other stuff that might sit on top of this. So, for example, we might be talking to a semantic web agent that tells us some facts, and we want to know, well, how did you arrive at that conclusion? How did you infer the thing that you just told me? So we'd like to have some way to describe proofs to people. So this is the chain of reasoning that I followed in order to work out this thing that I've just told you. Other things that we can do at this point is start looking at things like the security side of things. So can we talk about things like signing bits of semantic web data or encrypting them, signing them so we have things like non-repudiation. This is the person that said this and they can't deny it. Once we have these sorts of things, we can combine these together and properly allow us to attribute pieces of knowledge to given actors with a reasoning chain behind them, so we understand why they came to that conclusion. That then lets us do things like formulate a position of trust about that information. And on top of this, you then build whatever your applications are. Now, some of this stuff in the sort of, the trust and attribution space, some of this has gone through some of the standardization work. So Luke Moreau, who's one of the professors here, led the provenance working group that produced an ontology for being able to talk about things like workflows. Where did this piece of information come from? What was the process by which it was created? Who initiated that process? And so on. So there are little bits in these sort of trust and proof boxes which have been through the standardization process, but by and large, those are still areas of academic inquiry. And I'm going to leave it there, actually, and carry on tomorrow because we're at 1:45. Any questions, John? Or carry on in the next lecture. Any questions?
RDF 相关的东西吗？
Someone want to talk about
RDF 相关的。
资源怎么 D 图形加好像 R 是缩写答案不用忘了。
你们之前写过这相关的系统吗？
没。科班出身的人可能写过。
没有，这个可能更偏门一点是吧？
我可能是学后勤的。